Hello, this is FlippedHarber for Precalculus. In this video, we'll be taking a look at section 2.1, Functions. The topics for this section include relations and functions, the domain and range, function notation, independent and dependent variables, implicit and explicit form, the vertical line test, and the graph of a function. The objectives for this section are to determine whether a relation is a function, finding the value of a function, finding the domain of a function, identifying the graph of a function, and obtaining information from or about that graph of a function. The outline for this video, we're going to start by taking a look at determining whether a relation is a function. We'll take a look at the vertical line test. Throughout this video, we'll be using the function notation, something that you should be familiar with, but this will kind of serve as a review of that topic. We'll talk about the domain of a function. We'll talk about obtaining information from the graph of a function as well as obtaining information about the graph. And then we'll take a look at applications. Now, determining whether a relation is a function. To each x in the domain of f, there is one and only one image f of x in the range, which means that every domain value can only create one range value. So if we look at a couple mapping diagrams from our textbook, the first mapping diagram on the left, we see only one arrow coming from each domain value. But in the second mapping diagram, we see two arrows coming off of the domain value Maureen. Now that means that this relation cannot be a function. We can only have one range value created by every single domain value. So it's that double arrow that stops it from being a function. Now, graphically, we can run the vertical line test to see if a graph is that of a function or not. Vertical line test basically says if we can draw a vertical line that goes through the graph in more than one spot, then it's not a function. So again, looking at some graphs from our textbook, the top two are functions, the bottom two are not. The top two are said to have passed the vertical line test. The bottom two fail that vertical line test because we can draw a single vertical line. It doesn't even have to be a bunch of them. Just one of them is all it takes that goes through the curve in more than one spot. Now remember, the y-axis counts as a vertical line. So if you have a graph that goes through the y-axis in more than one spot, it's not a function. Now let's talk about the domain of a function. The domain are the numbers that we plug into the function, the x values. What I want to do is start by saying, okay, we'll start with the entire set of real numbers, and then we're going to narrow it down based on what is allowed or not allowed to be plugged into that function. Some things to remember. We can only have positive numbers under square roots. We can't have zeros in the bottom of a fraction, and quite often we're going to state our domain using an inequality. Now let's take a look at these two functions, h of x and g of x. Now first of all, they're in function notation. You should know that because you should recognize function notation from previous math classes. Whenever we have h of x or g of x or some other letter, we know automatically that it's a function. The question here is not whether it's a function or not. If it's not a function, it wouldn't be written in function notation. So we want to talk about the domain of these two functions. So let's start with this h of x function. We're going to start with the idea that it's all real numbers, and then we're going to whittle it down from there. We don't want to build it up. We want to take it from the big to the little. Now, what rule could I break accidentally if I don't pay attention to this? What values can I not plug in? Well, because it's a fraction, we know that the bottom, x minus 1, cannot equal 0. So I'm literally just going to make that statement, that the bottom of the fraction cannot equal 0. If I solve this, this will put a limitation on my domain. So x cannot equal 1. So now my domain value is a set of numbers, so I'm going to put it in set builder notation. That's where we take these squiggly brackets, and that's read the set of x such that, and now I'm just going to write my statement that I just found. X cannot equal 1. Now, whenever we use a exclusive event like this in set builder notation, we're excluding 1. It's understood by everybody that every other number is okay. That's why we start with all real numbers, because if x doesn't equal 1, then it must work. Okay, let's take a look at g of x over here. Now, we don't have a fraction, so we don't have that same limitation on x, but because it's a square root, we have the limitation that what's under the square root, that is 1 minus x, has to be greater than or equal to 0. So now if I solve this inequality, I'll have figured out what my domain is. So really, I'm just going to move the variable first. X is less than or equal to 1. So again, I'll build my set builder notation. So there we go. We've just talked about the domain for these two functions. Now, obtaining information from the graph of a function. Now, the first thing we really want to be able to determine is it even a function? So we'll run the vertical line test. We also want to be able to talk about x and y intercepts. And we want to talk about symmetry. Symmetry over the x-axis, symmetry over the y-axis, and symmetry over the origin. So let's talk about the first one. Is this really a function? Well, it's pretty obvious that it's not. I could draw a lot of vertical lines that go through this graph in more than one spot. Yes, there's vertical lines that don't go through the graph at all, but that's not the vertical line test. If I can draw just one vertical line that goes through in more than one spot, it's not a function. So this is not a function. All right. Now, what about our x and y intercepts? Our x-intercepts are where the graph goes through the x-axis. Our y-intercepts are where it goes through the y-axis. Well, it's pretty obvious this graph doesn't go through the y-axis. So there's no y-intercepts. But it does have two x-intercepts. And we can just if you want to, you can also give them as a point. You could say that the point 1, 0 and the point negative 1, 0 are the x-intercepts. I really don't care which way you go. Let's talk about symmetry. If a graph is symmetric over the x-axis, that means that for every point same x value, but an opposite y value. So this graph is symmetric over the x-axis. In order to test for symmetry over the y-axis, for every point that's on the right, this graph has that. For every point on the right side, there's a point on the left side that has the same y value, but the opposite x value. So this graph is symmetric over the y-axis. Our last type of symmetry is over the origin. And basically, what we want to see is if every point on the graph, there's the complete opposite. So for the point, looks like about 2, 2, is the point negative 2, negative 2 also there? For every point in quadrant 1, there's a similar point in quadrant 3. For every point in quadrant 2, there's a similar point in quadrant 4. So this graph does have symmetry over the origin. So this graph has symmetry over all three. Obtaining information about the graph of a function means that we should be able to answer some questions without actually seeing the graph. Now, we're going to see questions like, is a given point on the graph? Again, we're not going to see the graph. We're going to have to figure out, is this point on the graph some other way? They're also going to ask, given an x value, what is the point? Meaning they'll give us an x value, we plug it in, we find out the point that's on the graph. And kind of the opposite, knowing the value of the function, we want to find x. So if we know the y value, what's the x value? And finally, what should the domain of this graph be? All of these things help us make graphs, but to answer these questions, we're not going to actually look at the graph. All right, so here's our function. F of x equals x squared plus 2 over x plus 4. Our first question, is the point 1, 3/5 on the graph? Well, really, what I need to do is plug 1 into the function. That is, find f of 1. If it equals 3/5, then yes, the point 1, 3/5 is on the graph. So I'll go ahead and plug 1 everywhere into my function. And sure enough, 1 squared plus 2 is 3. 1 plus 4 is 5. So the point 1, 3/5 is on the graph of f of x. Now don't forget to actually answer the question. This is a yes or no question. The math proves it, but you have to answer it. Okay, B. If x equals 0, what is f of x? And what point is on the graph of f? So really, this is a lot like the previous problem. We're going to take 0 and plug it into our function, see what we get, and determine our point. So I plug 0 everywhere into my equation. I get 2/4. What is f of 0 equal to? It's equal to 1/2. What point is on the graph of f? Is 0. All right, part C. If f equals 1/2, what is x? Well, we kind of know the answer to this already. What we're going to do is we're going to take the function x squared plus 2 over x plus 4. We're going to set it equal to 1/2. And we're going to solve for x. Now, we already know one answer, but maybe there's more. So let's do a little bit of cross multiplying here. 4. I multiplied the 2 from the lower right up to the upper left equals. Now this is a quadratic. I'm going to solve it like any other quadratic. Let's bring everything over to one side. 2x squared minus canceled. Now this is nice for factoring. I'll just pull out my x. We have two solutions. One we already knew. If f of x equals 1/2, you can get that by plugging in 0. We knew that from part B. But there's another answer. And that comes from that other factor, 2x minus 1. So, if f equals 1/2, what's x equal to? It's equal to 0 or 1/2. What point is on the graph? Well, now, lastly, What is the domain of f? What numbers can we plug in? What numbers can we not plug in? I think we should be able to just write this right away as long as you recognize this is a fraction. We can't let the bottom equal 0. So my domain is the set at. Now what can I plug in? Well, there's my domain. All right, let's move along, and we'll take a look at an application. So here we have a table that tells us some time in hours and some distance in miles. Okay, part A asks, does the relation defined by the ordered pairs represent a function? Now really the easy way to decide this is, do we have any repeats in the domain? Now the domain is the t first. The time is our domain. So do we see any repeats in the time? No, we don't see any repeats. So this relation is a function. They want us to draw a scatter diagram of the data. So I've put up a grid here. We're basically just going to plot these points. So we'll include the point 0, 0. Okay, maybe not. We'll include the point 1, comma 30. Now, what do I need to go up by in order to make all of this fit? Well, we need to get all the way up to 300 on the y-axis. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 boxes. To make it fit somewhat nicely, I'll need to go up by 30s. So let's label it 30, 60, 90, and then 120, 150, 180, and then 210, 240, 270. So we'll mark the point 1, comma 30. We'll then mark the point 2, comma 55, right about there, a little bit shy of 60. 3, 83. Oop. We'll mark the point 4, 100. 5, 150. 6, 210. 7, 260. And finally, 8, 300. Okay, so there's our scatter diagram of the data. Now that should be done on graph paper. That should be cut out and put on your homework like always. We're going to select 2 points from the data and find an equation for the line containing the points. Now it really doesn't matter which 2 points we choose. I like to choose a point from towards the beginning and towards the end. So there's what I'll use. So normal slope calculation, our slope is equal to our change in y. So 300 minus 30 is 270 divided by our change in x. Okay? Now, we want to use probably the same 2 points and this slope in order to find an equation. Minus Now, interpreting the slope. Well, it's got a positive slope. So it takes more time to drive a farther distance. Okay, part E, we want to express the relation found in C using function notation. Okay, so I didn't change it into slope-intercept form yet. I want to go ahead and do that now and basically solve for that y. So we're going to move the 30 over. We'll be replacing that with an f of x in a little bit. Now, I add that 30 over, but I want to be able to combine it with this other fraction. 30 written as the appropriate fraction. So now, writing it as a function, just replace that with and combine these two fractions into one. So negative 2 over 7. Just leave it like a fraction. It's easier that way. Now, part F, what is the domain of this function? Well, it looks like it's all real numbers, but we need to stop and think about the context that this was given to us in. Our x value, which is actually a t, is representing time. What can't we have as far as time? Can we have small values of time? Sure. 1 second, 2 seconds. Can we have big values for time? Sure, we can have 24 hours, 48 hours. We can have weeks and weeks and weeks. What we can't have is negative time. So possible. It's even included in our table. Now, part G, we want to predict the distance that the car was driven after 11 hours. Basically, the tool that we made in step E, or if our graph is big enough, we could go ahead and try to make a prediction based on our graph. All right, so that's it. You've got your homework for the section. It's time to sit down and try it, and we'll try to finish it up in class. I hope you learned a lot. I'll see you in class, and I'll see you online.